Okay, we're going to solve some problems. I'm not going to read the problem and assume we've done that already. I want to first point out, though, they mention this thing conventional current. Well, by convention, we assume that when they just say current, the convention is to assume it's positive. And conventional current is just referencing that specific convention, make the current positive. Okay, so the positive charges are flowing this way. They said the electron is flowing in the same direction. There's the electron's velocity. And we want to know where the force is on the electron. Now, there are two ways to do this. Okay, you can first stick your thumb, we'll do it the long way first, stick your right hand, your thumb, along the direction of the charge, point your fingers up, and then curl them into your, this is hard to draw, but you want to curl them into your palm. Now, if I use my right hand, my thumb is actually behind the wire, right? This is all behind the wire, and my fingers would curl around like this, and then it would curl back like that. So if I draw a bigger loop, here's what the magnetic field looks like. It's curling around like this, down and around. This curling rule with the right hand tells us where the magnetic field points. And at this moment, or at this location, the magnetic field points straight down, tangent to that loop. Okay. Let me take away the hand. The B field points down. Now I'm going to find the force using my other right hand rule, the one where my palm faces with the force. I use my left hand because it's an electron. My thumb sticks in the direction of the velocity. So my thumbnail is on the other side. This is the inside of my thumb. And my fingers point down like that. And where does my palm face? This is my palm. It's facing out away. So this is the velocity again. Fingers point with the B field. Well, you just gained another finger. And the force points where your palm is directed. The answer is D. There's another way to do this. Kind of a shortcut. So here's the positive charge traveling this way. The electron is traveling here, but it would be equivalent, if it were positive charge, it would be equivalent to imagining a positive charge flowing in the opposite direction. So if you want to pretend that this negative electron is positive, you would just need it to flow in the opposite direction. Whenever we have positive current flowing in opposite directions, we've learned that there's a repulsive force between the two wires. And so that's another way to get to the answer of D. Okay. We've got two long wires going in the same direction. We've learned that when they go in the same direction, they attract. There's an attractive force. We could, figure this out, stick our thumb, our right hand, and curl our fingers in toward our palm, and we find that the field from X, the B field from X, X's B field points into the page all the way on this region of line X, current X. And over here, X's B field would point out of the page. Right? So if the field points in, you stick your fingers pointing into the page, your thumb points up, and your palm is facing to the right. That's how you would find the rightward force acting on these positive charges traveling upward. Okay. 3 parallel wires carry equal currents into the page. What's the direction of the magnetic force on wire Z? Well, they're all going in the same direction, aren't they? So if I just think about these two, they go in the same direction, there's an attractive force. Let me draw that again. They're pretty close to each other, right? So let me draw the force fairly large. Equal and opposite attractive force. Next I consider X and Z. they also carry current into this, both into the page, same direction. And if the two wires carry current in the same direction, they also feel an attractive force. But it's weaker because they're farther away, right? All right then, I sum up those two effects, and the total force on Z, unsurprisingly, points to the right. Oops! I circled the leftward. There we go. 3 wires carry currents into the page. All right, what's the direction of the force on P? Well, P and R carry current in the same direction, so the force is attractive. Oh, let me draw that again. P and Q also carry current in the same direction, so they similarly attract. And these two forces, red and purple, are equal in magnitude because they're all spaced the same distance and they all carry the same current. So the net force would be X. You can think about it like this. The X and Y components, we can break these forces into X and Y components. The X components cancel and the two Y's add together. It's like you would do, if you want the net force in the Y direction, you would take this arrow and stack it on top with this arrow, and the net force would be in the direction of arrow X. Okay. So we have to draw the magnetic field pattern due to this current. You stick your thumb up. It's your right hand because it's just current, so we assume it's positive charge. We take our fingers and we curl them around toward our palm, and that tells us where the field lines point. So we have then concentric circles going around like this, and the farther out we go, the more spaced they become. And we said they were curling this way. All right, we've got an electron traveling in this field. It's traveling to the right. We would use our left hand to find the force, but wait a second. Q, V, B, sine theta. The charge is moving to the right. The field points to the right. The angle between those is 0, and sine of 0 is 0. Sine of 0 degrees is 0, and the force is nothing. You need some perpendicular motion through the field. At least a component has to be perpendicular to feel this magnetic force. Okay, this is a cool one. A little complicated, but here's what's happening. You've got like a scale, which I like to think of like this, right? And then there are these two wires, one here and one here. They carry current in opposite directions, right? You turn on that current, and the question is, what happens to the reading on this scale? Well, if the forces repel, then now more pushes on the scale and the reading goes up because there's more pushing down on the scale and it registers more force. But if the two wires attract each other, if the force were attractive, then now the weight of the wire is being relieved from the scale and the reading would decrease. So what happens when they're in opposite directions like this? Well, when the currents are in opposite directions, the forces are repulsive. The wires repel. And so we would see there's more force pressing on the scale, and the reading would increase. And you would just explain, the wires are going in the wires carry current in opposite directions, so the force on the wires is repulsive, and this bottom wire then pushes down. There's more force pushing the bottom wire down into the scale, which increases the reading. Which of the following will not give rise to a magnetic field? Ooh, a magnetic field. That means, you've got charges moving, or there's current carrying a bunch of charges along, and those charges, use your right-hand rule to figure out, oh, like it curls around this way. Let's see, it would be this way. And that field extends out, right? Like this. But not always will we get this magnetic field curling around, forming a sort of cylinder. So when won't we get a field? Well, a neutron sure looks like it. It's not a charge. To get this circular field, this cylindrical field, you need the particles that are moving to have some electric charge. All these would produce magnetic fields.